Greetings, geometry advanced scholars. I hope you had a great weekend. We are finishing up lesson 11.1. One thing I do want to emphasize with circles, if you're a person who plans to maybe focus on the SAT for standardized test, at the end of the SAT, they always ask circle questions. It's kind of like they're big, like, ooh, you really know what you're doing if you can do circle questions. So make sure you're on top of those. But first thing I want to do is a quick review. You learned all the different parts about circles, like secants, tangents, diameters, chords, all the different names that you had. And then we were working with the common tangent. And one thing that we realized, there's two different types. We have the external common tangent, which are the ones drawn here in red, and then you had the common internal tangent, which is drawn in blue. And then you were introduced to this first theorem, and it said the following: if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. And so you always need to get in the habit of marking the right angles, and it does not want to mark it for me, and I'm not sure why. So we'll just do it like, here we go. Let's see if it'll be a little bit better if I do this. All right. Always draw in the right angle. And here's the reason why, guys. When you do that, if you notice, if I draw the radius to the point of tangency, it will form a right angle. Now notice if I take the center to that point, what type of shape did I just form? A right triangle. So it's going to be really critical that you understand lots of right triangles are going to come out when you work with this one. And here's the really cool part, is if I continue drawing that, right here, I get another right triangle, and those two right triangles actually end up being similar, but we're just using this first theorem. But that theorem also goes the other way around. It has its converse, and it says the following: if a line is perpendicular to the radius of a circle at the point on the circle, then the line is tangent to the circle. So this is just going the other way around. All right, so here's the thing. The moment you know you have a tangent line, you want to draw in your radius to that point of tangency, and you're going to want to draw a right angle no matter what. So let's do some examples of this together. All right, here's the directions. It says, assume that the lines that appear to be tangent are tangent. Point C is the center of each circle. Find the value of x. Well, if we do like what we've been saying, and we always draw in our right angle, no matter what type of triangle did we just form? Yeah, we just formed a right triangle, and now we can quickly solve for x. So to solve for x, we know it's an acute angle of this. So you have 90 minus 58, and that is going to end up being 32 degrees. So pretty quick and easy to get. Another way you could have done that, remember, is you can have gone x plus 58 plus 90 is equal to 180, and you would still get the fact that x was equal to 32 degrees. I don't really care which one you do, long as you show me the work. What did I just say? Yes, I just said that magic thing called work. Please show it for me. Now on the next one, you have a couple different things that you could apply. I advise doing it the way that I'm going to explain it to you. There are some ways that you can do it differently, but a lot of people struggle with getting it consistently right when they do so. But when you're looking at it, I hope you guys would agree with me that this right here, you would agree, would make a lovely quadrilateral. And with that quadrilateral, we can draw in our radius to the point of tangencies, and we get two right angles, and we're given one angle at the central angle of this circle of 130 degrees. We should know that the angles of a quadrilateral add up to 360. If not, don't forget you can use n minus 2 times 180 to find that it's 360 degrees, because remember, you just go n, which is the number of sides of the polygon, times 2 times 180 gives you 360. But what makes this so nice now, I can just go x plus 90 plus 90 plus 130 is equal to 360 degrees. And you're going to end up solving for this, and x is going to end up being 50 degrees. Now, a few people say, hey, Gregerson, can't I just divide this perfectly in half? Yes, you could do that, but you actually create more work because then you have to use an angle bisector, then you have to solve for one of the acute angles, then you have to double it back. So it's really not the best way of doing that problem. All right, now let's do some other stuff that comes as a result of working with the fact the radius to the point of tangency forms a right angle. So again, it says in the diagram, ray AB is tangent to circle C at point B. Find the value of x. Well, here's the cool thing. If I put x in right there, I have a right triangle. And we know, since the radius is x, that the whole length of the hypotenuse ends up being x plus 2. Well, with right triangles, how do we solve for missing sides when we don't know angles? Well, we always do the Pythagorean Theorem. And so we go leg squared plus leg squared equals hypotenuse squared. Okay, so we get here on the left, we get x squared plus 64. But the hypotenuse being squared is what you're really doing is foiling. We're going to go write it off here, off to the side here. X plus 2 times x plus 2. You are multiplying those together using distribution, or we use a term called FOIL to remind you to do the whole thing. And you are going to get x squared plus 4x anytime I start videoing. It works fine when I'm not videoing. All right, anyway, so notice it becomes a trinomial. Listen to me, scholars. You will see this again on assessments. You will have to understand that a binomial being squared is going to give you a trinomial. So please don't forget to use it, okay? So we get here x squared plus 64. I'm going to rewrite that, x squared plus 4x plus 4. And then we're going to solve for it. So what do we have to do? Well, we're going to subtract x squared from both sides. It's a quadratic, so we think, oh, probably have to factor. But once you do that, you end up getting 64 is equal to 4x plus 4. Subtract 4 from both sides. You get 4x. X in this case is going to be 15. Now I want to show you something. If that's the case, you guys see that we have a triple, an 8, 15, 17 triple. Kind of cool, isn't it? Okay, let's keep on going. All right, the middle example here. A lot of people say, oh, we can't do it. We don't know the radius, but if the radii of a circle is congruent, so we know this one is 3. And I know I have my right angle, and that makes the hypotenuse 10. So make sure you actually put the hypotenuse in the right location, please. It's always opposite the right angle. And then we do the Pythagorean Theorem again. 3 squared, I don't know why it's doing this, my friends. I'm trying. 3 squared plus x squared is equal to 10 squared. So we get 9 plus x squared equals 100. X squared is equal to 91. And then we just take the square root of both sides. Don't forget your plus or minus. X is going to be the square root of 91 because we want positive length. All right, let's look at the last one here. Okay, using the same type of a concept as the last couple problems, the radius to the point of tangency, we always draw in a right angle. Now, those of you who are probably fast forwarding to this, I need you to pause for a moment and listen to me. You must draw in that right angle or you'll get problems wrong. And I will look for that and I'll take off points for it because this is something I'm really emphasizing that you must do. Also, don't forget that the radii of a circle are congruent. So when I work with this, I should be able to solve it very quickly. Now, there's the long way and then there's the short way. This time I'm going to do the short way first. Guys, this is a right triangle, correct? If I have a leg that is 9 and a leg that is 12, what is the hypotenuse of that triangle? It's 15. It's a 9, 12, 15 triple. So x plus 9 would equal 15 and x would equal 6. Or you could do like what we did earlier and go leg squared plus leg squared equals hypotenuse squared. And so we end up getting 81 plus 144 equals x squared plus 18x plus 81. My friends, we end up moving everything to one side of the equation and we realize you'd have to factor. It would factor into a positive and a negative. You would have a -6, and we'd have a +24. And then we would solve, setting them both equal to 0. X would equal -24. We couldn't have a negative length, right, my friends? And x minus 6 is equal to 0. X is equal to 6. So we could do it the long way. I don't know about you, knowing your triples sometimes pay. Now, just warning you, you might have to factor, so don't forget to use this. All right, then we have one last thing we're going to do, and then we're going to some examples with it, and I love this example. It says the following: if two segments are tangent to a circle from the same external point, so they have to come from the same location. So just like these two, here would be your external point. Then the two segments are congruent. How could we actually prove this? And the reason why this works, my friends, is because the hypotenuse leg congruence. So let me show you real quickly. Right now it doesn't want to let me go to my... I love when things don't want to go my way, but hey, we'll throw it in there anyway. So we draw in the two radii to the points of tangencies. We draw in both right angles, and then we draw in the segment that connects the center to that external part. Notice we just created two right triangles, and the cool thing is those two right triangles are congruent because the hypotenuse is congruent by the reflexive property, and then we have the two congruent legs because of the radii. So by hypotenuse leg, those two triangles are congruent. And then, oh yes, by corresponding parts of congruent triangles being congruent, we show that the two other legs are going to be congruent, which those end up being the tangent segments coming from that external point. So guys, a lot of factoring and stuff can happen with these. You need to make sure you're staying on top of this. So with this one, quick, easy example, notice they don't always show, and both of these examples that you see here on the screen are kind of strange, but they don't always show well if something's tangent or not. So it's just, if it looks like it's tangent, you're gonna have to go with it. But the thing is, when you look at that and you see that two tangent segments are coming from the same point, you just set them equal and you solve. So like here, I know as a fact that segment HG is equal to segment HK because they're two tangent segments from the same external point. So we just go 4a plus 2a is equal to 5a minus 32. And then we solve. Why did I say 4a there? It should be 4 plus 2a equals 5a minus 32. So we equals 3a on the right, and I'm going to add the 32 to both sides, so I get on the left 36. So I get 36 is equal to 3a. We solve for a, and I get that to be 12. But I'm looking for the length of segment HG. That's where I want to go. So we go 4 plus 2 times 12. So that's 4 plus 24, which equals 28. So HG is length of 28. Now, the exact same process is done for the next example. So let's just save us some time, my friends, and we're going to set them equal to each other. Now, notice this has decimals, so it's okay to have decimals, but now we're just going to sit there and I would put this over 1 and I'd cross multiply and solve. So if you do that, you get x is equal to 4x minus 25.2. Subtract 4x over. Solve for x. X is going to be 8.4, but we have to solve for the length of segment RS, so we plug it in. 8.4 all over 4 is 2.1. All right. Now, here's kind of fun, but we're going to apply this concept all together. And by the way, this is the same as the first two problems on homework. So if you haven't gone through these notes too quickly, you had just heard me say these are the not exact same problems, but the process that you need for the first two problems on the homework. So I advise doing that. But notice what they did is they drew tangent lines or tangent line segments that intersect with each other in order to circumscribe this circle. But the thing is, the rules don't change. And all I want to know is the perimeter of each, which means I need to know the length of all of them, and I don't know the length of this line segment. But I can use the idea that if tangents are tangent from the same exterior point, they're congruent. So I'm going to use that idea, and I'm first going to use the idea that I know that those two are congruent to each other. So when I do that, if this one's 6 inches, this one also has to be 6 inches. Well, if that's the whole line segment over there is 9, doesn't that leave this segment right here to be 3 inches? So since we took out 6 away from that, we left it to be 3. We also know this segment right here has to be the exact same length because they're 2 tangent segments from the same one. So these two are going to be the same with each other. So this is 3. But then what does that leave for that line segment right there? That's right, 5. Which means on this other side, what is the length of that segment? Because they're from the same exterior point. 5. So what's the length of that whole side? 6 plus 5, which is 11. So the perimeter is really 8 plus 9 plus 11, which is going to give us 28. And don't forget your label, inches. So let's use the same type of idea when we're working here on number B. Now, we have a couple missing ones, but the thing is we can get there pretty quickly. For instance, if I know this segment is 6, I know this one end up having to be 6, which leaves the segment to be 4, which, as we know, these 2 tangent segments are going to be the same length, so that's 4. So the length of this side is now 9. So we're getting closer. And then we're going to go now and use the fact that if this segment is 5, this segment right also is 5. And so we know that's going to be 5. Well, if that's 5, and let's do a different color. Let's do right range here. If that's 5, that leaves this segment to be 7, which means this segment has length 7 because they're tangent segments from the same exterior point. Well, that makes this segment right here 4, which means this segment over here, which comes from the same exterior point, is also length 4. Oops, here we go, length 4. So the cool thing is that I know now the length of this segment of that pentagon ends up being 10. Now I can find the perimeter of that pentagon because I know the length of all the sides. So we get 10 plus 9 plus 12 plus 11. And if we add those all together, we get 23 plus 9, that's 32. I got 52. Got 10 plus 10 would be 52 feet. And those are just fun to do, but it's making sure you understand that if you have 2 tangent segments from the same external point going to the same circle, they're always going to be congruent. Guys, there's some tougher problems on the homework, but you should be able to do a great job with them.